Trigonometry is the study of the relationship between the sides and angles of triangles. We define basic trigonometric ratios using the lengths of sides of a right-angled triangle. Let's say we've been given a right-angled triangle ABC with the angle C equals to 90 degrees. We call the side that is opposite the 90 degrees angle, the side AB, the hypotenuse. So the side that is opposite the 90 degrees angle in a right angle triangle will always be the hypotenuse. And we call the side that faces the angle of interest. In this case, we have the angle theta. So the side that faces the angle theta, the side AC, we call it the opposite side. And the side that is closest to the angle of interest, the angle theta, we call it the adjacent side. We use these sides of a right-angled triangle to define the basic trigonometric ratios. We define the sine of theta as the opposite over the hypotenuse, the cos of theta as the adjacent over the hypotenuse, and the tan of theta as the opposite over the adjacent. The following example demonstrates how we express the trig ratios when given the lengths of the sides of a right-angled triangle. You've been given PQ equals to 13 units, PR equals to 12 units, and QR equals to 5 units. And we are required to find or determine the following trigonometric ratios. Now the sine of theta, yes, theta should be given by the opposite side to theta over the hypotenuse. That will be 5 over 13. And the cos of theta, this is the angle theta, will be given by the adjacent side over the hypotenuse. That will be 12 over 13. Remember, the hypotenuse never changes. It's the angle that faces the 90 degrees angle. Now, the tan of theta is given by the opposite of theta over the adjacent of theta. Now, to find the sine of alpha, here's the angle alpha. Remember, sine of an angle is the side that faces the angle over the hypotenuse. So the opposite side to the angle alpha is 12. So that would be 12 over the hypotenuse. The hypotenuse never changes. The cos of alpha will be given by the adjacent over the hypotenuse. So the adjacent side to alpha is QR. So it will be 5 over 13. And the tan of alpha will be given by the opposite over the adjacent, which will be 12 over 5. We can extend these definitions to any angle by plotting any point on the Cartesian plane. In this way, we can rewrite the trigonometric ratios in terms of x, y, and r. Let's say you've been given some point P, which is some r distance away from the origin. So if given this as a circle, r will be the radius of this circle. Now that's the distance that our point P sits away from the origin. And we've been given the angle theta. If we complete this right-angled triangle, this side will be given by x, and then that side will be given by y, which are the points of, the coordinates of the point that we've been given. We can use this right-angled triangle to find the trigonometric ratios in terms of x, y, and r. The sine of theta will be given by the opposite over the hypotenuse. Our opposite to theta is y, hypotenuse never changes. The cos of theta will be given by the adjacent over the hypotenuse, and the tan of theta will be given by the opposite over the adjacent. We can also use the theorem of Pythagoras. If you look, we have the right angle triangle. We can use the theorem of Pythagoras to find r. Now, the theorem of Pythagoras says the square of the hypotenuse equals to the sum of the squares of the other two sides. So the square r squared will be equals to x squared plus y squared. Now, in this example, we are given a point P with coordinates 2 and 3 in the first quadrant. We are asked to find the value of sine theta, cos theta, and tan theta without using a calculator. First, let's complete the right angle triangle by joining point P to the x-axis. If we place the coordinates of P to the sides of this right angle triangle, we will have 3 as the opposite side to theta, and then we'll have 2 as the adjacent side to theta. This is the x value, this is the y value. We can use the theorem of Pythagoras to find r, the radius of these units of this circle, or the length of P. Now, the theorem of Pythagoras says the square of the hypotenuse equals to the sum of the squares of the other two sides. So r squared or OP squared is given by x squared plus y squared. We can simply substitute the values to find the value of r. In this case, r will be the square root of 13. So r is the square root of 13. Now, in this right angled triangle, we have all the sides. We have all the sides. Now, we can use the sides of this right angled triangle to express these three trigonometric ratios. We know that the sine of theta is given by opposite over the hypotenuse. Therefore, the sine of theta will be 3 over the square root of 13. And the cos of theta is given by the adjacent over the hypotenuse. Adjacent over the hypotenuse is x over r. That will be 2 over the square root of 13. And the tan of theta is given by the opposite over the adjacent, which is 2 over 3. Let's try another example. Please feel free to pause the video and try solving the problem by yourself. In this problem, the coordinates of P are given as k and 1, and the radius as the square root of 5 here. So P is k and 1, and the radius is the square root of 5. Now we are required to determine the value of k. We can use the theorem of Pythagoras to find the missing value of k. If you look at the information that we've been given the value of r, we've been given the value of y, so the only missing value here is the value of x. So we can use this theorem of Pythagoras to actually calculate the value of k. Now we can simplify that to have k plus minus 2, k equals to plus minus 2. Now you look at the Cartesian plane. K is the value of x is positive in this first quadrant. So we call this is the first quadrant, second, third, and fourth quadrant. In this quadrant, we have the positive x-axis and the positive y-axis. So k would have been positive in this part, but x in this quadrant and this quadrant is negative. Therefore, k can only be minus 2. Here we are given the point P with the coordinates minus 5 and 12 in the second quadrant. We are further given a point S with coordinates A and B in the third quadrant, such that the angle TOS is given by theta plus 90 degrees, and the length of OS, or the length of the arm, the terminal arm from the origin to S, is 6.5 units. We are required to calculate the value of b, the coordinate or the y coordinate of s. Here is our point S. The point S sits some 6.5 units away from the origin. It's given by A and B, and it makes an angle of 90 degrees plus theta, or theta plus 90 degrees. Remember, from here to P, we have theta, then we add 90 degrees to arrive at S. Now we can start by joining by completing this right angle triangle, so that we can find the length of OP or R, which might come in handy when we're solving this problem. So to find the value of OP, we use the theorem of Pythagoras. We've already been given the value of X and the value of Y for the coordinates of P. We can simply substitute that to arrive at 13. So R is 13. We can also complete this right angle triangle here, so that we can be able to find the value of b. Now remember, b is the y value in that regard. So we know that in this right angle triangle, the sine of theta plus 90 degrees will be given by the opposite, which is the b that we're looking for, over the hypotenuse. In this case, we will only have one unknown, which is b. So we can show that by saying the sine of theta plus 90 degrees equals to b over 6.5. Now, we are going to talk about the core functions in the next sections that follow in this series of trigonometry. Now, the sine of theta plus 90 degrees, or 90 degrees plus theta, can be written as the cos of theta using our understanding of core functions. Now, the cos of theta, we can find it using this triangle, which we already have enough information for the angle theta. The cos of theta will be given by the adjacent over the hypotenuse, which is minus 5 over 13, equals to b over 6.5. We can actually cross multiply this in order to find the value of b, which is minus 2.5.